will see this setup. We have again, after the preamplification stage, we have high pass and low pass filtering. So these filters will actually eliminate the interference signals like your electrode half cell potential and the preamplifier offset potentials also. It will reduce the noise amplitude by limiting the bandwidth of the amplifier. Because the biosignal should not be attenuated or it should not be lost. There should not be any distortion. So the higher order sharp cutting linear phase filters have been used here as high pass and low pass filters. Again, we have a isolation amplifier here. This is done for the purpose of separating the biological signal and interference. So it will decouple the patient from the measuring equipment and it will provide safety from the electrical hazards. It also prevents galvanic currents from limiting the or deteriorating the signal to noise ratio by actually preventing the ground loop system. We will see the details of isolation amplifier in detail. So this various principles are involved to realize this isolation stage. We will see the either using a transformer or coupler to provide a isolation barrier. So digital isolation amplifiers, they use voltage or frequency converter to digitize the signal before it is transmitted. Then the most important characteristics of the isolation amplifier is low leakage current, isolation impedance, isolation voltage, and then we have rejection or CMR, and the maximum safe isolation stage. So we'll see to that now. So this is about the differential amplifier that is used in the amplification stage. Okay. So next we will see about the interferences. So what are the interferences caused in the differential amplifier? So this is the most critical part in the measuring the biosignals. So this may be due to the contact between the electrodes and the biological tissue. So both the electrode offset potential and the electrode tissue interface are subject to changes due to the movement, that is the artifacts. Here we call it as the artifacts. So as such, two interference signals are generated as motion artifacts. First one is the changes of the electrode potential, and second one is motion induced changes of the voltage drop caused by the input current of the preamplifier. Okay, these are the possible two interferences that may be generated. So these motion artifacts may be minimized by providing high input impedances for the preamplifier or usage of non-polarized electrodes with low half-cell potentials. So the non-polarized electrodes such as silver chloride electrodes may be used. And then we can reduce the source impedance by using a proper electrode gel. Okay, so the motion artifacts, interferences from external electromagnetic fields, and all the noise generated by the wires connected between the electrodes and the amplifier, all these can be reduced by using twisted pair cables, shielded wires, and input guarding. Okay, so this recording of the biopotential is often done in an environment that is equipped with many electrical systems. So when we say many electrical systems, there is probability of producing strong electrical and magnetic fields. So we can say, in addition to the 60 Hertz power line frequency interference signals, some other strong harmonics or some high frequency electromagnetic fields can also be generated as interference signals. So the electric and magnetic components of the interfering fields can be considered separately. So the electric fields are all caused by the conductors with no flow of current. The current will be very minimal. So the current is actually capacitively coupled into the body, so it flows to the ground electrode. Okay, so if proper isolation is provided, or if an proper isolation amplifier is used with the patient ground, the current is can be capacitively coupled to the ground. So the body potential floats with a voltage of up to 100 volt towards the ground. So minimizing these interferences will require to increase the distance between the power line and the body, and using a proper isolation amplifier. So it provides the separate grounding of the body at a far away location from, that is, the meshing electrode will be little bit far away from the human body, and using a proper shielding for the electrode cables. So next is need for calibration. Why do we need to calibrate differential amplifier? Okay, so this is the calibration stage is the final stage, final requirement of the bioamplifier. So first one is, since the amplitude of the biopotential is determined, it has to be, the amplitude has to be determined very accurately. So there must be provisions to easily determine the gain or the amplitude range reference to the input of the amplifier. Okay, so that is your first requirement, easy determination of gain. So for this purpose, the gain of the amplifier must be well calibrated. So in order to prevent difficulties with calibrations, some amplifiers that need to have adjustable gain with a number of fixed gain settings rather than providing a continuous gain controls. And then some other amplifiers have a built-in standard signal source. So they have a standard signal source of known amplitude built in them. So this can be momentarily connected to the input by the push of a button. We can have a button control. So this standard signal can be given as input with the use of the button control. We can check the calibration at the output of the potential amplifier. This is self-calibration. Okay. So next we will see about instrumentation amplifier. So this is a kind of differential amplifier with additional input buffer stages. So the addition of input buffer stages uh, makes it easy to match the impedance matching of the amplifier with the preceding stage. So the useful features of the instrumentation amplifier are low offset voltage, high CMRR, high input resistance, and high gain, all these. So this is a we have three op amps here. This is the differential amplifier circuit. So we have three amplifiers set up. This actually forms the instrumentation amplifier circuit. So the output from the transducer is given as, the transducer will give you the digital signal. So electrical signal, sorry. So this will be given as input to the instrumentation amplifier. So before the signal goes to the next stage, a special amplifiers is required. So with high CMRR, high input impedance to avoid the loading effects. So this high CMRR, high input impedance amplifier is nothing but an instrumentation amplifier. So this will satisfy all the required processes. So you have two differential amplifiers here. To each input of the differential amplifier, a non-inverting amplifier is connected. So the amplifier on the left side, if you see, it will act as non-inverting amplifier. They are combined together and they will form the input stage of the instrumentation amplifier. So the third amplifier, the third op amp is the difference amplifier. It will generate the difference of both, output of both op amps. So this will be your output of this difference amplifier will be the total output of the instrumentation amplifier. So this V out is the difference between the two input signals given at the input point. So V01, suppose we take the output from this first amplifier as V01 and the output of the second amplifier as V02. So this V0 will be R3 by R2 into V01 by V01 minus V02. This acts as the difference amplifier. So this is the three different circuit realizations of instrumentation amplifiers used in biomedical applications. So this is your voltage follower input stage, and this is the amplifying input stage, and this is your 2 op amp version of the three different configurations of the instrumentation amplifier. So if you take this to if whatever the requirement of the instrumentation amplifier is to vary the gain, so the resistor can be replaced with the resistance can be replaced with a suitable potentiometer. So the instrumentation amplifiers, they are actually used in situations where high sensitivity, high accuracy, and high stability are required. So they are usually made like this with the three op amps here. Okay, three op amp setup. So this three op amp setup which is shown here has many advantages, like the cost is very, the design of this amplifier is very low, and the CMRR, that is the common mode rejection ratio of this setup, is very high. And then the accuracy, the high accuracy can also be achieved by replacing, instead of this resistances, we can replace its resistances by metal film resistors. Okay, so um, what happens, the linearity, the amplifier will, the output of the amplifier will be linear, so there's good linearity, typically about 0.01% for a gain of less than 10. So the output impedance also becomes low, that is in the range of milliohms. The input bias current of the amplifier is between here, this the first op amp and the second op amp. So the output generated will be with a gain of R3 by R2 into V01 minus V02, which is the uh, output of the first amplifier and the second